This is section 5.3, and we're going to talk about exponential functions. So suddenly x is not being raised to a power or nothing's being done to it. It is the variable that is the exponent. So that's a little bit different than what we've had. So the basic form, f of x equals c a to the x. A is the base that's being raised to the variable x. C is the coefficient, the leading coefficient. Now those are some basic parameters. A has to be greater than 0, because if it were 0, you would no longer have a function. It doesn't need to be 1, because 1 to any power is still 1. You'd have a horizontal line. And C has to be greater than 0, because otherwise it would all go to 0. So here's some examples of exponential functions written out. And so if you're asked to tell me what the base is, remember it's the only thing being raised to the x. So in this power, in this example, the base is 3. This one, I want you to realize that the only thing is being raised to x is 5. So you can't say, oh, that's 10 to the x. You don't ever get to do that. This is one separate thing. So the base is 5. Here the base is 1/2. It's whatever's being raised to the exponent x. All right, let's see the difference between an exponential and a linear function. This is 2 to the x. This is 2 times x. So 2 times x is a linear function. And as x gets bigger by 1, the 2x gets bigger by 2, the y part, and so you have that average rate of change. Now here, 2 to the x, this shape looks like this, and you're going by 1 here, but here you are going up exponentially, and so we get higher and higher pretty quickly. So that's the difference in those. Now, you can have either exponential growth, which looks like that, or you could have exponential decay. There's a lot of applications that have exponential functions in them, including financial applications. So we'll be looking at some of those as we go through the chapter. Some properties of this, the domain of it is all reals, because it's going to go all the way here. But if you'll notice, the range is 0 to infinity. It doesn't exist down here. Now, you could do something to the function, and it could be down here. But your basic one, no x-intercepts. The y-intercept is that c value. And for this one, if a is positive, you're going to increase there. If it's between 0 and 1, in other words, if it's a fraction, it's going to be decreasing on its domain. So those are just some things to think about. Now let's look at the financial. So compound interest. When you put money in the bank, in a savings account that's compounded, they compound the interest, and they may do it for a certain period of time. They may do it quarterly or monthly. It just depends. But this is the formula. Now, nobody is sitting in the bank doing that by hand, but that formula is built into some sort of computer software that is doing that. So this is how we will have to do some of this by hand, but we'll also use our calculator, so it won't be too bad. So this is the formula. Here's what each piece is. A is the accumulated or future amount. So if you put $100 in, whatever you end up with at the end, that's your A. P is the principal. That's that $100 that you started with. R is the interest rate. And say if they're doing it at 5%, you have to put it in decimal form in your formula. T is the time in years. So if you had a problem that talked about 18 months, you would have to make that 1.5 because it's in years. So remember that. N is the number of compounding periods. Like I said, you could be doing it quarterly. That would be 4 times a year. Annually would be 1. Monthly would be 12. Semi-annually 2. So it won't, it'll say one of these words. It won't tell you that that's in, so keep that in mind. The other formula is continuous compounding interest, and it is A equals P times the number E to the RT. And E is a number that's pretty important. We have it on our calculator. Let me get my calculator up here. It wasn't open, so let me get it open. Okay, so I've got it up. Now, if you look down here at the ln key, that's the natural logarithm. There's an e to the x. So if you knew that you wanted to raise it to something, you could do second and the ln key. If you just needed the number e, it's right here. So if I did second and hit the divide key, I've got e, and if I hit enter, I get the decimal evaluation. Now, it is like pi, and so we usually end up rounding it or just using the e to be exact. But it is on our calculator, so let's keep that in mind. All right. Modeling half-life. I think we might have one problem on half-life. It's kind of like it's an exponential, but you have this 1/2 here. So it's c times 1/2 raised to the t over k. K is the half-life in years, T is the time in years, and C is the amount of the element. If you've had chemistry, you may have studied half-life of elements, and so that would be where that would be an application. So I think that'll get us going on the notes for that. Let's go look at the problems. Some of this is on your calculator. It says do it without a calculator, and you certainly could do either one, but you should be able to do it without it. So if you have 5 to the negative 2, that's the same. If you, that negative 2 can become positive if you switch positions. So that would be 1 over 5 to the positive 2. That's 1 over 5 squared, so that's 1 over 25. If you have 8 times 36 to the 1/2, we need to remember that 36 to the 1/2 is the square root of 36, which is 6. So 8 times 6 is 48. So we can do these without our calculator. Now 25 to the 2/2 times 25 to the 1/10. 25 is the same base, so we can add those exponents. So we have 25 raised to the 2/5 plus 1/10. Well, 2/5 is equal to 4/10. And so 4/10 plus 1/10 is 5/10, which is 1/2. And 25 to the 1/2 is the same as the square root of 25. So our answer is 5. So we got a common denominator here and changed 2/5 to 4/10. And then we added it and we came up with that. Use the zero exponent rule to simplify. Well, anything to the 0 power is 1. So 2 to the 0 is 1. 7 to the 107 to the 1 over 17. Well, power to power, we multiply. That's different than adding. This was multiplying two bases and we added. But power to power, we're going to multiply. And 107 times 1 over 107 just leaves 1. So that ends up being 7. Number 6. Following an unexplained decline in the number of birds of prey on his property. What are birds of prey? Be like hawks and eagles and owls that eat little animals. So a farmer sees a dramatic rise in its small mammal population. So if the bird of prey, if there aren't as many of those, then probably the mice and the little rabbits, those things would start growing. So this function, 500 times 1.5 to the t, can be used to estimate the number of small mammals on the premises within t years if hawks, owls, and similar birds fail to come back. Estimate the number of small animals in the area 4 years after the decline. Well, that just means we're finding m of 4. So we're going to plug 4 in for the variable t. So you'll do that on your calculator. 500 times 1.5 raised to the 4th. And it says round to the whole number because we don't have a part of an animal. So we have 2531 there. Number 7, approximate this to 4 decimal places. If f of x is 6e to the negative 1.4x and x is negative 1.2. So let's do that one on the calculator just so you can see what that looks like. I'm going to move over this much so I can see. And so I've written it right here for what you should put in, but let's just do, whoops, hello. Let's go back. All right, so let's clear that. And we've got 6, and we want the e. Remember, we want it right here. So second, and that ln key gives us 6e. Now we have a box up there. We're going to do negative 1.4 times, what are we doing? Negative 1.2. So times negative 1.2. That's all up in that box. And we hit enter. And I have 32.1936. I don't know where the 4, oh, so 1, 2, 3, 4. I see 32.933. I don't know if I put something wrong or if that answer's wrong. Let me check that real quick for you. Okay, I did it 2 different times, and I am not sure why I have that there. So it could be a little bit different. Check yours when you're doing it real carefully, because I am not sure what happened there. But I feel like right now it's 0.1933. So I don't know. I don't think I put anything weird. Anyway, be real careful when you're doing yours. All right, approximate this one. 1/7 e to the x minus e to the negative x, for x is negative 1.4. So you've got 1/7 parentheses e to the negative 1.4 minus e, and then it's negative x, which just makes that positive, so put in 1.4. When you do all that, you should get negative 0.5441. Number 9, graph the equation on paper and then choose the correct graph. So you could do it on paper or you could do it on your calculator. Let's go here and go to y equals, clear, and clear, and go back up here. And this is 5 raised to the x. And we're going to do a zoom 6. See if we get it. Okay. And that's a. So you could throw it in your calculator and get it pretty easily. If you did 4 to the negative x, you're going to get this one. And then there is 5 to the x again. I don't know why that's repeated. 12, 4 parentheses, 1/5 to the x. You should get this. Then they ask you to graph one with the graphing tool. And so I've given you some steps. You want to enlarge the graph and choose the exponential tool because it's 4 to the next x. And so that's that tool right there. Then click on the origin. So you would click in the middle here. When you do, this box comes up. And it is reflected, since that's a negative x, it's reflected across the y-axis. We're going to click that box, and we're going to save and check, and you should get that. So hopefully that will help you in getting that. And the base should be down here. So the one I was doing, I guess, on my example when I pulled it up in homework, had a base of 6. But double check that your base is correct down here. This one is 4. I'm not sure what you'll have in your homework, but you can check the base there. And you would do the same thing here, except this has a horizontal shift because up here in the exponent, we've got x plus 3. And the base is e. So you should get the same kind of things. You've got a horizontal shift over here of 3, and your base will be E. So just the same kind of thing. Number 15, use the compound interest formula to determine the final value. So they're saying we're going to put $250 in, 3%, which is 0.03, and we're going to compound it daily. Well, daily would be 365 for your N, and then 13 years. So here's the formula. A equals 250 times 1 plus 0.03 over 365 raised to the 365 times 13. It'll always be rounded 2 places. They've got the dollar sign there, so you round to the nearest cent. Okay? Now, there is an app on your calculator. So I'm going to show you that real quick, and you're welcome to use it anytime. So let's quit out of here and clear. And we have apps. Where's my apps? We're right here. So we go to apps. The first one is finance. If you have an older calculator, you may not have all of these, but I think even the old ones have that finance. So enter, and we'll choose TVM Solver. All right, N is not just the 365, it is the total number of compounding periods. If you're doing it for 13 years, that's 13 times 365. So let me get that. So 365 times 13, that'll be 47.45. See if this works. Interest rate, you do not have to put it in a decimal, so we just put 3 here. The present value is 250. Put that there. Payment, we don't have to worry about a payment. This is what we're going to solve on, future value, so we're going to leave that alone for a minute. Payments per year, this is where we'll put our 365, and it should just put it down in the CY. And now we'll go back up to future value, and we want to solve on that. So we're going to hit alpha and enter. And did we get that? 369.24. Okay. So, and the reason it is negative here, I think, it always ends up negative, is that the bank's paying you that money out. That's future value for you. It's coming out of their money. So you ignore the negative, and it's 369.24 rounded. You're welcome to use the app, or you're welcome to do it by hand. Now, the continuous interest you cannot do with that app, so you would have to do this one by hand. It says $400, 9% interest compounded continuously. That tells you it's the PE to the RT for 11 years. So 400 E to the 0.09 times 11. You should get 1,076.49. Number 17. We've got $1,100, 11.7% compounded monthly for 2.5 years. So that's P is 1,100, 1 plus 0.117 over 12, raised to the 12 times 2.5. And where did the 12 come from? That's the monthly that we're doing. And you should get 1471.66. Number 18, compare investing $27.50 at 5% compounded monthly for 20 years with investing $27.50 at 6% compounded monthly for 20 years. And they want you the final amount after 5%. So if you do 5%, you get $74.59.76. If you do 6%, so the only thing that changed was the interest rate, you get that. Subtract these two to get this number here. So 74.59 goes here, the 91.03 would go here, and then you subtract them to get the difference. All right, number 19, this should be our last. A fish fly density is 3 million insects per acre and is decreasing by 1/2 every week. Estimate their density after 3.3 weeks. Well, remember C is your initial, A is your decay factor, your rate, and X is the increase in time. So for this problem, C is 3 million, A is 1/2 or 50%, that's 50%, so we use 0.5, and then you have an X. So here's our general formula. And then it says estimate it after 3.3. So you're just putting 3 parentheses 0.5 raised to the 3.3. And you should get 0.3 million per acre. Okay, because it's decreasing, so that makes sense. We have 0.3 million instead of 3 million. So that's just using the decay function and putting the pieces in there. So 19 questions, but some of them go fairly quickly. But that'll get you going on exponential functions.